The last thing we're going to talk about in this 2 week chunk is a really brief point that I want to talk about. It's not, it turns out, all that central to anything we're going to do going forward, but it is a useful concept to be aware of. And that concept is equipotentials. This isn't the first time we've seen something like equipotentials. We have seen isobars and isocores and isotherms before, these lines in some graph somewhere that were at constant temperature, pressure, volume, whatever they were. This time, we're going to have constant potential, okay? And they have some nice interactions with the electric field, as it turns out. Okay, so if I have some charge, Q, I've got an electrical field leaving Q. Sorry, I'm going to have to draw a few of these. There we go. That electrical field tells me something about the lines where the forces are and things like that. But there's running around this also kind of set of lines that are closely related called the equipotentials. They're lines of constant potential, okay? And here's the rule for equipotentials. They're always perpendicular to field lines, okay? If you think about it, it should make sense. If I move along a field line at all, I'm changing my electrical potential energy, okay? If I move up the field line, my electrical potential energy is going down. If I go the other way, it's going up, assuming I have a positive charge. The only way I can move with this field and not change electrical potential energy is to move perpendicular to it. So if I know the shape of the field lines, I just got to draw some pattern that's always perpendicular. In this case, a circle, okay? There's a whole set of circles around this that are all equipotentials at different potentials. This might be 1 volt, this might be 2 volts, this might be 3 volts, and so forth. This might be 4 volts. It keeps going out farther and farther and farther. Technically, for these even spacings, I actually know for this one that my spacing would actually have to change as I go out. That's because of what we talked about in the last video, but I didn't feel like carefully spacing these. Okay, so what's the value here? What's the use of this? In this case, it looks really stupid simple because they're all circles, but what's the value? First of all, if I take a charged particle and I move it along an equipotential, it doesn't gain or lose any energy. It costs me nothing, no work at all, to move a charge along an equipotential, okay? There are lots of times when that's going to happen, okay? Charges inside a conductor will try to move along an equipotential once the field is negated, for example, because there's no work being done. The other value is it gives you an idea of the shape of the field in some sense, okay? This is like a topographic map of the field. Each of these curves represents some constant height equivalent in the field. The field lines represent directions of steep descent. So if I wanted to show people what's the steepest way to go up or down some hill, I would use the equivalent of the field lines. If I was trying to show them how to move at a constant height, kind of around the edge of a hill, I would use equipotentials. So let's try a more complicated case. As you may recall, we have done the field due to 2 plus charges, and it looked something like this. And this one was doing the same thing. I apologize, it takes me so long to draw a field. So the question is, what do the equipotentials here look like? Well, let's start with this one. Really close in, things look a lot like a single point charge, and so they're going to be kind of circular. Okay, but as I move farther out, the equipotentials are going to have to start merging. Okay, at some point, I'm going to have maybe another circle, but at some point, I'm going to have equipotentials that encompass both of these. Okay. As I get farther and farther out, this gets less and less lumpy and rounder, and as I get infinitely far away, I end up just getting a circle that includes both of them very near the center. Okay. So somewhere in between, there's one that does something like this. You notice I'm trying to maintain kind of a more or less perpendicularity to the field lines at every single point. Okay, it's hard to do with hand drawings because I'm a terrible artist, as you know. But I'm trying to convey that. This is what this would look like. Now, in the lab, you can do this. You are going to do this, or you perhaps already have done this, depending on when you're listening to this, by actually just tracing your probe. You're going to have some kind of probe, and you're going to trace it along and try to keep a constant value and just record what points you're finding this constant potential at. Okay? But that's telling you the shape of the electric field another way, because once you have the red curves, you can draw the perpendicular black curves to that and see the field. Okay, so that's another one of the advantages of the equipotential lines. All right, that's all I have on equipotentials. I will see everybody in class.